Hi, my name is Kira Donovan, and I worked with Amy Arrington and Janina Edmonds on this project. We chose to use MATLAB to model the spread of disease. For our model, we looked at COVID-19 specifically since there is so much data on this disease. Epidemiological models are useful in predicting how a disease or similar diseases might affect a population. These models are not only useful to scientists and medical professionals, but also to the general public. They can be used in educating individuals on the best ways to prevent infection and transmission. The specific model that we chose to use is called the SEIR model. The SEIR stands for susceptible, exposed, infected, and recovered or removed. We looked at how the number of individuals in each of these categories changed over time during the COVID-19 pandemic. This is the basic SEIR model and the parameters that we used on this project. These were obtained from quantecon.org. Beta is the rate of prolonged contact between individuals if one is infected. Sigma is the infection rate, and gamma is the recovery rate. The first equation in the basic model represents the flow of individuals from susceptible to exposed. The second equation, which represents the total number of exposed individuals, the change in the total number of exposed individuals per time, is represented by the flow into exposed minus the infection rate times the number of exposed individuals. The third equation is the change in infected individuals per time, which is the number of exposed individuals times the infection rate minus the recovery rate times the number of infected. And the fourth equation is the change in recovered individuals per time, which is represented by the recovery rate times the number of infected individuals. The parameters that we used are experimentally found values specific to COVID-19.
My name is Amy, and I'm going to be talking through solving the model in both a simple and more complex case. In order to solve our model, we stuck our systems of equations into ODE45. This simple model function takes the three inputs, parameters x and t. Time is not used in this model as r0 is time invariant. The function just creates our system of equations in ways that can be used in ODE45. When looking at cumulative caseload, your R0 value can no longer be time independent. Because the contagion changes due to a wide variety of factors, including things like vaccinations or lockdowns in the case of COVID, the R bar n function can be changed based off the new contagion value for R0. Similarly to the simple function, the cumulative caseload function, f for simplicity, takes all of your parameters and puts them into a matrix that is usable by ODE45.
Hi, my name is Janina Edmonds, and I'm going to discuss the results and conclusion of our project. Our first graph shows the overall SEIR model with each of the populations displayed. As you can see, during the first days of the pandemic, the susceptible population was at 100%, while the exposed, infected, and recovered populations were at 0%. The populations stayed this way until about day 145, where the exposed and infected started to increase, therefore causing the susceptible to decrease and the recovered to increase. After the 350 days, the exposed and infected populations had gone to 0%, while the susceptible was near 100% and the recovered was near 0%. This is due to the herd immunity that the overall population had gained after being exposed to or infected with the virus. Our second graph shows how the SEIR model changes when the basic reproduction number changes. The basic reproduction number represents the average number of secondary infection cases that are generated by a single primary case. When the reproduction number increases, the model shifts to the left, which means the different disease populations begin changing at an earlier time. This also means that the entire model from start to finish will occur in a shorter amount of time, which can be seen in the top right and the two bottom graphs. Our third graph shows the cumulative caseloads for the infected and removed individuals over the pandemic time period. As you can see, the infection and death caseloads both increase exponentially, which is expected because all of the individuals that became infected either recovered or died from the virus. This means the infection rate is proportional to the recovery and death rate, which can be seen in this graph. In conclusion, our model accurately displayed how COVID-19 spread among populations of individuals across the world. Our model is very useful for further understanding how diseases spread and how epidemics can be prevented. In addition, our model is versatile, meaning that it can be applied to any other disease that is represented by the same parameters that we used. Overall, our team gained knowledge about how differential models can be applied to engineering and real-world situations, and we observed how these topics will be valuable in our future jobs. Here is a list of our references, and we would like to thank you for listening to our presentation.